Good morning, friends. I hope everyone is doing well. I request everyone to watch my videos in a sequence. In the earlier videos, I have discussed what is a control hazard and how to handle the control hazards with the help of two techniques such as delayed branching and branch prediction. In this video, we will discuss another technique to handle the control hazards. Now, before discussing what is the technique, let me discuss with an example. I have I0 instruction, I1 instruction, I2 instruction till I9. So I have 10 instructions are there and I am executing these instructions using a 4-stage pipeline. Meaning is that I have stage 1, stage 2, stage 3, stage 4 are the 4 stages are there in a pipeline. So what is the meaning? If you want to execute any instruction, it has to go to these 4 stages to complete its task. Now let's take that I0 is there in the location 100, I1 is there in 101 location, I2 is there in 102, I3 is there in 103, so on. Is it clear? Now let's take that I2 is a branch instruction. Let's take that it is a branch equal instruction R1, R2, 2000. Is it clear? This is the address. Let's take that. What is the meaning of this instruction? It is telling that branch equal R1, R2, 2000. What is the meaning of this one is when this condition will be, this is a condition. Are you able to understand? So what is this condition is saying? If R1 and R2 is equal, the values which are there in the register R1 and register R2 is equal, then the condition is true. If they are not equal, the condition will be false. If the condition is true, then you have to go to the address location 2000 and fetch the instruction which is there in the 2000 location. Let's take that instruction 200 is there in the address location 2000. So if the condition is true, then you have to execute the next instruction as I2000. If the condition is false, you have to execute this instruction I3. Are you able to understand? So you need to wait till you know that whether you have to execute the instruction I2000 or I3. Is it clear? So now what I will do is that let's take that this result I will come to know after stage 2. Okay, this result I will come to know after stage 2. Then how this stage time analysis diagram will looks like. What is the stage time analysis diagram? It will tell you how the instructions are executing in the pipeline. So in the y-axis you will have the stages, and in the x-axis you will have the clocks. Okay, let's take that. So you are executing I0. How you will execute? You will execute I0 instruction like this. In the clock number 1, you will execute it stage 1. Then you will execute the stage 2, then stage 3 and stage 4. So at the 4th clock cycle, it completes all the operations. Are you able to understand? Similarly, I1 will be executed during this one. Okay. If you does not know how I have done, I request you to watch my previous videos. Okay. Now let's take that I2. I2 is a instruction where you will execute like this. Why I am doing like this? See, if you see that at the 2nd clock cycle only stage 1 has completed its instruction 1. Am I right? Then at the clock cycle 3, stage S1 is free. So that's why I have started executing the instruction 2. Similarly, it will apply to all the stages. Now let's take that. This result, whether I have to execute the next instruction is I2000 or I3, we have discussed that it will come to know after the 2 stages. Meaning is that here I will come to know. Am I right? Because now I will come to know here whether I have to execute I2000 or I3, I will come to know here. Am I right or wrong? So what I have to do? If it is a delayed branching technique, then what we have done? We have introduced the stall cycles. Meaning is that we are not performing any operations during these clock cycles. Are you able to understand? Then if let's take that if this condition is true, I would have executed I2000 instruction. Am I right? 8th 9. Is it visible for you? I hope it is visible for you. Okay, like this I would have executed. Now let's take that if it is a delayed branching, what I am doing, I am introducing the stall cycles. Meaning is that I am not performing any operations here. If I am not performing any operations here, then what will happen? The number of clock cycles required to complete all these instructions will be more. If we are taking more clock cycles, then meaning is that the performance of the pipeline is degrading. Are you able to understand? So that's what is happening in the delayed branching. Now can we overcome this situation? So how can we overcome? Instead of wasting these cycles, we can execute some instruction. If we can execute some instruction here, then let's take that I9 up to I9 is there. So I4 to I9 instruction is there. So if we can execute any instruction which is there from I4 to I9 here, then we are not wasting the clock cycle. Then you can ask me, sir, which instruction I will execute? You have to execute the instruction such a way that if you reshuffle any instruction, let's take that I8. Now, if I have to reshuffle this I8 instruction, when I can reshuffle is, if I reshuffle that one, the performance of the, not performance, the output of the program will not vary. Am I right or wrong? If the output of the program will not vary, I don't have any problem. If the output of the program will vary, then only the problem will occur. Let's take that I8 is an instruction. If I reshuffle it, then there is no problem. Similarly, I7 instruction also, if I reshuffle, what is the meaning of reshuffling? You are executing at this stage. So, if you find such instructions, if we implement them during these clock cycles, if your program output is not varying, then we can easily execute them. So, introducing the stall, instead of introducing the stall cycles, what I will do is that during this clock cycle pulses, I will execute the instruction I7. Similarly, I will execute the instruction I8. Meaning is that I have reshuffled them and I have executed them. Is it clear? So, if I do that one, I am not introducing any stall cycles and I am executing the instructions which are there in this program. Then, obviously, the performance of the pipeline will not be degraded because it will not take more clock cycles to execute these 10 instructions. I hope you have understood how we have to select the dummy instruction. We are not selecting any dummy instruction. You can say that, sir, you have selected I7 and I8. Your pipeline architecture should be intelligent such a way that it should be able to identify. In one of the next video, I will discuss one gate question, how we can select such instructions which will not affect the output of the program. Such instructions we will executing during this clock pulses. Okay, I hope you have understood whatever I have discussed in this video. If you still have any doubts related to this concept, feel free to ask me in the comment section. I will try to clear your doubts in less than 24 hours. Thank you for watching my video. Have a nice day.